Okay, welcome back. This is chapter 11 on infinite sequences and series, and this is going to be section 11.8 on power series. So, what is a power series? A power series is a series, but it's of the form where you've got an infinite sum of c sub n times x to the n, where c sub n is an expression in n. And they're considered the coefficients of the series. So you've got this extra variable x to the n, which gives the description of what type of series it is. And that is a power series, because we remember that a power function is one where f of x is equal to x to the n, where n is a member of the whole numbers, right, or the natural numbers, positive values of n, whole numbers. So we're going to be looking at these types of series, which actually look like an infinite polynomial. X, if we just for a second suspend our c sub n, which is going to be an expression in n that describes how we can formulate the coefficients of our power series. Let's just take for a second, if c sub n is equal to 1 for all values of n, then we would have a power series of x to the n. And x to the n, if we just went and evaluated the first couple of terms, this would be n equal to 0, this would be n equal to 1, this would be n equal to 2. And you can see that that looks like an infinite polynomial. We also know from geometric series that if absolute value of x is less than 1, then this series here is going to converge to a over 1 minus r, where here in this instance a is equal to 1 and r here is equal to x. So if we were to substitute those values, we'd get 1 over 1 minus x. Good. But a power series in the most general form would be almost like a horizontal translation of our original power series, c sub n times x to the n. If we were to horizontally move it by a units, value of a, let's say for instance a was equal to 2, and if we were to move it to the right by 2 spots, then we would get c sub n times x minus a to the n, and that is your most generic power series, and we would still have that the x minus a to the n would still be a power function. Good. All right, so right now we've got an infinite polynomial, so let's talk about what is the domain of a power series. And the domain of a power series is going to be all of the values of x, where if we were to substitute that value of x into our power series, it would turn it back into a numerical series like what we have been studying. And if that numerical series converges, then that value of x is part of the domain of that power series. Does that make sense? So we will be talking about what are the collection of values of x that when substituted into our power series makes our power series converge. And so that will be known as its interval of convergence. And we're going to find out that for any given power series, there's only 3 possibilities. And that is that the series will only converge for x equal to a. And notice if we were to take that value of x equal to a and we were to substitute it in here, inside the x minus a to the n, then we would have a minus a to the n, and a minus a is 0, and 0 to any power is 0, and 0 times any c sub n is 0, and the sum of 0 is 0. So it would be a convergent series, and any power series is going to be convergent at that x equal to a. Now backing up, in that generic or general power series of c sub n times x minus a to the n here, we call that a power series centered at a, or a power series that about a. Good. And we will learn later on that the usefulness of power series is to be able to represent functions as power series around that value of A. We can use our power series as a nice approximation to our curve, and that approximation will be an infinite polynomial, of which we can approximate with a finite partial sum there. Good. Another possibility for our interval of convergence will be if the series converges no matter what value of x we have, and we're going to figure out when we can determine if our power series will converge no matter what value of x we substitute into the power series. And then finally, we will actually have a range of values of x where a would be in the center of that interval. And so we would be identifying a radius of convergence around A. So I want to read that here in this next page. The number r in case 3 above is called the radius of convergence of a power series. And by convention, the radius of convergence is r equal to 0 in the case of I. So I can write that up here. Our r here would be equal to 0. And if it converges for all x, we would say that our radius of convergence is infinite. And in the third case, we would have that our r is equal to r. And that is our radius of convergence here. So how would we find those things? So let's do a couple of examples here. In general, to find our radius of convergence, we usually use the ratio test or the root test and force convergence for our power series. So if we look at our ratio test, what does it mean for a series to converge? And if we use our ratio test, that means the limit of our a sub n plus 1 over a sub n will go to a limit that is less than 1. So we want to actually force convergence and then find the values of x. Good. So this is how we will do that. And I believe the first two instances here, we're going to get either case 1 or case 2. And I actually want to move forward and do a case 3 first. So let's take a look at this one where we see if I were to break apart this and put it into a more clear scenario to identify what your C sub n is. I just rewrite this as the sum from n equal to 1 to infinity, and I'm just going to group together the n expressions. So I have minus 1 to the n times n squared times 4 to the n, and then I have times x minus 1 to the n. So this portion here, all of the n expression, is what we would call the C sub n. And we have here the x minus 1 to the n, and this scenario, this is our x minus a to the n. So we see here that this is a power series centered about a equal to 1. Okay, or it's about a equal to 1. Good. So they're asking here, find the radius of convergence and interval of convergence. And remember, we're going to be using either the ratio test or the root test and forcing convergence. When do you want to use the ratio test? You would like to use the ratio test when we have exponentials like a 2 to the n or a 4 to the n or a 7 to the n, or instances where we have a factorial. When would we want to use the root test? We would want to use the root test if we have an expression in n raised to the power n. So in this case, I see n squared. I also see 4 to the n. So I'm actually going to use the ratio test and force convergence. Because we're trying to find the interval of convergence, so we want our series to converge. So if I take the limit as n goes to infinity of a n plus 1 over a sub n, I'm going to get the limit as n goes to infinity of an plus 1 times 1 over a sub n, which is the limit as n goes to infinity of, and what is my a sub n plus 1 expression? Remember, your a sub n plus, or a sub n, is the entire expression inside of that summation. So I'm going to say that that is minus 1 to the n plus 1 over n plus 1 squared times 4 to the n plus 1, and then I have times x minus 1 to the n plus 1. That is my entire a sub n plus 1. It's the entire expression, but wherever n appears, I substitute n plus 1. Now I'm going to take the reciprocal of that with my a sub n. So whatever was in the denominator of my original expression is now in my numerator. And I have times n squared times 4 to the n over minus 1 to the n times x minus 1 to the n, absolute value. So now I have a fraction, and I can begin to cancel common factors in the top and bottom. And I see that n fours cancel with n plus 1 fours to leave 4. One value of 4 left over. I see that n factors of x minus 1 cancel with n plus 1 factors of x minus 1 to leave 1 factor of x minus 1 left over. And I can do the same with the minus 1s, but remember, since I'm inside absolute values, it's irrelevant to even include the minus 1s, but you can go ahead and do that. But n minus 1s cancel with n plus 1 minus 1s to leave 1 factor of minus 1 left over. And now I'm going to group all of my n expressions together and all of my constants together in my limit as n goes to infinity. And remember, when the limit as n goes to infinity, in that operation, n is the variable, which means in our expression inside the absolute value, x is actually a constant. So I'm going to group here. This is going to equal the limit as n goes to infinity of the absolute value. And I see that I still have n squared, and I see that I have n plus 1 squared, and I see that I still have in the numerator that minus 1. If you still want to include it, it's okay. And for the sake here, since I did include it, I will. And I have over 4 in the denominator, absolute value. Now, I'm taking n as n goes to infinity. I don't really want to use L'Hopital's rule, but I'm going to transform my n squared over n plus 1 squared into a composition by using my exponent rules. And I see that I have n over n plus 1 squared times minus 1 x minus 1 over 4. And I know my limit laws. The limit of a composition is the composition of those limits, provided that the outside function is a continuous function. And here the outside function is x squared, and that is continuous. So if I go inside and take the limit as n goes to infinity of n over n plus 1, I know that that is going to go to 1. You can either do L'Hopital's rule or factor out the highest power of n to get that response. And now, when I take my limit as n goes to infinity, I am going to the absolute value of 1 times negative 1 times x minus 1 over 4. And remember, I want to force convergence. So I want to say that this is less than 1. Good? I can see with my minus 1, I do know that I can factor out that minus 1. And I can say that this is over absolute value of 4 times x minus 1 less than 1. And if I were to solve for the x minus 1, I get that the absolute value of x minus 1 is less than 1 times 4, which is 4. Good. This is the expression that you want to move towards because we have a power series that is centered about a. So we want to get to an expression of x minus a less than r. So I now know from here that my radius of convergence is equal to 4. And that's how you find your radius of convergence. Now I want to actually find my full interval of convergence. I want to find the maximum values. And really, with this expression here, I do know that absolute value of x minus 1, less than 4 does translate to minus 4 less than x minus 1 less than 4. That is my initial interval of convergence, but I want to find the range of values of x. So I want to put x as the center of my range, so I'm going to actually solve for x in this compound inequality by adding 1 to all three sides, and I end up with minus 3 less than x less than 5. And this is my initial interval of convergence. Good. Now, the endpoints are going to be the case where x is equal to, or where our ratio test is equal to 1, and that will give us an inconclusive result. So what we want to do now to get our final interval of convergence is to test our endpoints, right? So we do want to test the endpoints for convergence to get the final interval of convergence. And this is where we go back to all of our series tests. I'm going to add a page here. And I'm going to test my interval of convergence. So for x equal to negative 3, I'm going to take my minus 1 to the n times x minus 1 to the n over n squared times 4 to the n from n equal 1 to infinity. And wherever x appears, I'm going to substitute my value of negative 3, and it's going to transform my series back into a numerical or a series of number terms. So I have minus 1 to the n times negative 3 minus 1 would be minus 4 to the n over n squared times 4 to the n. And now I'm going to just manipulate that expression. And I end up with n equal 1 to infinity of minus 1 to the n times minus 1 to the n times 4 to the n, just factoring out that negative 1 from the minus 4 to the n expression. And the motivation behind that is for me to cancel the 4 to the n's. And I do see that negative 1 to the n times negative 1 to the n is going to be minus 1 to the 2n, which is always going to equal 1. So I'm just now going to reduce my series to be n equal 1 to infinity of 1 over n squared. And I know that this is a convergent series because it is a p series with p equal to 2, which is bigger than 1. So I do know that if I go back to my initial interval of convergence, that x equal to negative 3 should be included in the interval of convergence because it converges at that point. All right, so let's test x equal to 5. So for x equal to 5, which is the other endpoint, I have n equal 1 to infinity of minus 1 to the n, and wherever x appears, I'm going to substitute 5, and so 5 minus 1 does equal 4 to the nth power, and times n squared over 4 to the n. And here I don't have to do any real algebraic manipulation other than canceling common terms in the top and bottom, and I end up with an alternating series, which is minus 1 to the n over n squared. And we know here that b sub n is equal to n squared, and this is a series that converges by the alternating series test. So x equal to 5, our series, that was an endpoint of our initial interval of convergence. It also converges there. So this too should be included in the interval of convergence. So our final interval of convergence is going to be -3 less than or equal to x less than or equal to 5, or you can write it with closed intervals notation. Okay, so when x is in that range, and note here with our a equal to 1 and our radius of convergence equal to 4, notice here that if I went 1, that's my a equal to 1. If I went +4, 1 plus 4 would give me 5, and 1, and back in the other direction, -4. 1 minus 4 is going to give me -3. So you see that our interval of convergence, your a value in your power series, x minus a to the n, your a is actually going to be in the center of that interval. Good? All right, so let's back up to the other examples that we have up here in this one. It says determine the radius and interval of convergence for the power series. So notice here that I see an n to the n. This is when you might want to use the root test when you have an n expression to the nth power. So if I'm going to use the root test and test for convergence, and force convergence actually, because I want to know what values of x will make my power series converge, I'm going to use the limit as n goes to infinity of the nth root of the absolute value of a sub n. And this is going to give me the limit as n goes to infinity of the nth root of n to the n times x to the n. And you will see that that is the limit as n goes to infinity of, and I can use absolute values here, n times x to the n. And now that's going to give me the limit as n goes to infinity of n times x. X is a constant, and n is the variable, and that is going to go to infinity times x, which is going to equal infinity, and infinity is never less than 1. So that tells me no value of x is going to make this series converge. So I have that my radius of convergence, my r here, is going to equal 0. And my interval of convergence, where it's centered at a, is only going to be the value of x equal to a, and in this case, x equal to 1. Right. Or no, x equal to 0. 1 was down below. Right? When x is equal to 0, every term becomes 0, and the sum of zeros is a convergent series. All right, let's take a look at this one. You're going to find out later on that this is a series that converges to the function e to the x. But I see an n factorial. When I see a factorial, I would want to use the ratio test and force convergence. So here I use the ratio test, and I'm going to use the limit as n goes to infinity of a sub n plus 1 over a sub n, and that's going to give me the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n, so that's going to be times n factorial over x to the n. And remember that n plus 1 factorial is the same as n plus 1 times n factorial. So when I cancel common factors here, if I cancel my n factorial with n plus 1 factorial, I'm just left with a factor of n plus 1 left over. And when I go to cancel n x's with n plus 1 x's, I have one factor of x left over. And in making that calculation, I tend to group my n variables together, or my n terms together, and I group my constant terms together, and in this case x is going to be my constant term, and using the limit as n goes to infinity, x is constant. And now when I take my limit here, n is going to go to infinity, so 1 over n plus 1 is going to go to 1 over infinity plus 1 times x. And this is going to go to 0 here, so 0 times x is going to go to 0. And 0 is always less than 1. And since this tells us that no matter what value of x I choose, this series is going to converge. So what value x to the n over n factorial converges, because we saw from the ratio test when we forced convergence, it's still at 0. We get a limit of 0, and 0 is always going to be less than 1. So that tells us that our radius of convergence, r, is going to be infinite. And if I were remembering that my value of a, and in this case, x to the n is the same as x minus 0 to the n, which is our x minus a to the n. So this is centered at a equal to 0. If I have my a equal to 0 and I go up infinity and back infinity, because that is our radius of convergence, I have that my interval of convergence is all real numbers, or in other words, minus infinity to infinity, or in other words, you can write the symbol of the real numbers, that script r. Okay, that concludes for now. We will continue the worksheet later, but I think this is a nice introduction to power series and finding the interval